Okay, let's do another problem involving use of the tables, in particular properties for ideal gases. Let's do one involving use of some tables. Let's say we have air in a rigid container. Now this rigid container, so what does rigid mean? It means the volume is constant, it can't be distorted. This air in this rigid container initially has a temperature T1, a pressure P1, and a volume V1. And then heat is transferred in such a way to cool down the air to bring it to T2. So in a rigid container, we start off with some temperature T1, and it gets cooled, or the temperature is brought down to T2. Let me give you some numbers here. Initially, the air is at a temperature of 500 degrees Kelvin. The pressure is 0.25 megapascals. That's 2.5 bar. So it's approximately 2.5 atmospheres. And the volume is 3 cubic meters. The final temperature is 300 degrees Kelvin. So we're cooling the air down by transferring heat. Okay? So what are we supposed to find in this problem? We're supposed to find the pressure once the air has been cooled down to temperature T2. And we're also supposed to find the heat transfer required to cool down the air. So Q1 to 2. Find the heat transfer, find the pressure at the final state. Okay? We'll deal with assumptions as we go along here. We'll deal with assumptions as we go along. Okay, let's get started. Let's get started here. Analysis. Analysis. Well, so we want to find the heat transfer. The energy balance is a place where heat transfer comes in. So why don't we write the energy balance for our air system? By the way, before I get started, let's make sure we define our system here. You need to know what you are applying the energy balance to. So our air is our system. Air system. So the air inside the container is our system, all right? So let's apply the energy balance. Q 1 to 2 minus W 1 to 2 is equal to the change in total energy from state 1 to state 2. And that's equal to delta U from 1 to 2 plus delta KE from 1 to 2 plus delta PE from 1 to 2. Change in internal energy, potential, and kinetic energy from state 1 to state 2. Okay, let's whittle some of these terms down and see if we can get rid of some stuff. Okay? Notice that we're supposed to find the heat transfer to or from, maybe Q1 to 2 will be negative, so we're supposed to find the heat transfer to or from the air. So this is what we're supposed to find. So let's attack this term. The work. What sort of work is involved with this situation? Well, remember there are 3 forms of work as far as you're concerned at the moment. There's boundary work, shaft work, and electric work. You see any wires in this problem? Any resistors in this container? I don't see any, so there's no electric work. Are there any shafts in here? Is there a propeller in here that's spinning around and applying a torque with some angular velocity and therefore transferring work in the form of shaft work into the system? Nope, I don't see any shafts, any propellers or impellers, so there's no shaft power or shaft work. What about boundary work? That has to do with the change in volume of the system, the work that the system does as it expands or gets compressed. One's positive, one's negative. It says it's a rigid container. Rigid container. I take that to mean constant volume and therefore no boundary work. So rigid container. So this implies to me that it's an isochoric process. Make sure my Yep, isochoric process, constant volume, and that implies W bound equals 0. Rigid container, isochoric process, no boundary work, no shaft work, no electric work. So I'm just going to write here W1 to 2 equals 0. No work. No work. Okay, so let's go to our energy balance here and we'll cancel that term out. No work. That's gone. Okay, let's attack some of the other terms here. The change in internal energy has to do with the change in either phase or temperature of the system. The temperature of the system is definitely changing, so I don't think I can get rid of the delta U term. But I can, I think, neglect the change in kinetic and potential energy of my air system. I don't get any sense in the problem that the air is moving, that it's accelerating, that it's slowing down, and I certainly don't get a sense that the position of the tank or the rigid container is moving. So there's no change in gravitational potential energy of the system. So I'm just going to assume these away. I'm going to assume these away. So I'm going to write here in my assumptions. This is where the assumption section starts coming important. I'm going to write delta KE 1 to 2 is equal to delta PE 1 to 2, and I'm going to set those both equal to 0. Starting to run out of room there already. Okay? So this implies Q1 to 2 is equal to delta U 1 to 2. All right? Now, I'm going to be using tables here to evaluate the change in internal energy. Let's have a quick look at these tables. Here's one out of the text. If you go right after specific heats, which we discussed in the previous lecture, you will see table B11, ideal gas properties of air. Enthalpy, internal energy, these are specific enthalpy and internal energy are a function of temperature. So we're interested in specific internal energy values here, and they're going to be changing for our system as it cools down. So I need to rewrite the delta U term on the right-hand side of the energy balance in terms of change in specific enthalpy, a specific internal energy of the system. So I need to write this as the mass of the air in my system times delta lowercase u from 1 to 2. And so that's going to be equal to the mass of the air in my system minus U2 times U2 minus U1. Okay? Now, I don't know the mass of my system and I don't know the internal energy. I'll tell you what, before we get too far into this, let's calculate the pressure at state 2. Let's just do that. I forgot we were supposed to do that. I kind of got ahead of myself. So let's calculate the pressure at state 2. So how are we going to calculate the pressure at state 2 before I do the heat transfer? Well, why don't we assume ideal gas behavior? We can check it if we want. So I'm going to write here, oh boy, I'm out of space, but I'm going to start loading more stuff up here. How about we assume IGB valid? Ideal gas law valid. If IGB is valid, then I can use the ideal gas law. So let me write the ideal gas law. So IGB valid. So pressure times volume is equal to mass times the gas constant times T. Okay? Now, how can I get pressure 2 without doing a whole bunch of work? Without doing a whole bunch of work here. How can I get pressure 2 without doing a whole bunch of work? How about I evaluate the ideal gas law at state 1 and I divide it by the ideal gas law at state 2. PV1 equals mRT1. And now I'm going to divide it by the ideal gas law at state 2. P2 V2 mRT2. Now, a couple of things. The m and the r can be canceled out. They're constants, the gas constant for air and the mass of the air. Also, the volumes are the same. V2 is equal to V1. Why? Because it's an isochoric process. V2 is equal to V1. Why? Because it's an isochoric process, rigid container. So V2 is equal to V1, and we can cancel out the volumes. Okay, so what does this imply? I'll take the P2 over here, and I'll flip the T1 and the T2 and put it over on the other side of the equation and then flip the equation. So I have P2 is equal to P1. And then I have T2 over T1 right there, okay? Now, what is P1? P1 is 0.25 bar. And T1 is 500 degrees and T2 is 300 degrees. So I know everything. Equals 0.25, megapascals. T2 is 300 degrees Kelvin and T1 is 500 degrees Kelvin. Remember, you got to put temperatures in Kelvin. Temperatures are given in Kelvin. But whenever you're using the ideal gas law, remember temperature is absolute, so it's got to be in Kelvin or Rankine, okay? Kelvins cancel out, and I get megapascals. So let me crank this out. 0.25 times 300 divided by 500. 0.25 times 300 divided by 500. And I get 0.15 megapascals. So P2 equals 0.15 megapascals. Let's box that up. Okay, that's a fairly easy calculation. Notice I did a bunch of algebra. I tried to be a little bit smart with my algebra so that I didn't have to go through and at least not yet calculate M and R and all that sort of stuff. Okay, I just did some cancellations. All right. Okay, so we got the pressure, P2. Let's get back to calculating the heat transfer. Let's calculate the heat transfer. I don't know a lot of things here. I don't know the mass of my system, and I don't know the internal energies at state 1 and state 2, specific internal energy. Let's see if we can calculate some of these things. Let's go to table. Let's go back to the table and look at the specific internal energies of the air at 500 and 300 degrees Kelvin. Let's see here, specific internal energy, air, 300 degrees Kelvin is 214.07 kilojoules per kilogram. 214.07, so let me write that down over here on the board. U2 is U evaluated at temperature of 300 degrees Kelvin, and that's 214.07 kilojoules per kilogram. And that is from B, what's the table? B11, okay? And 500 degrees, 359.49, 359.49, 359.49. So U1, 359.49 kilojoules per kilogram. And that's U evaluated at 500 degrees. Let me get this off here so you can see what I'm writing. Okay, so I've written the specific internal energies from table B11 at 300 degrees and 500 degrees. So now we can plug it into our energy balance. I have these two now. I have U2 and I have U1. The only thing is I don't have the mass of my system. Oh, where are we going to get the mass? Well, let's use the ideal gas law. Let's use the ideal gas law. Let's see here. PV equals mRT. So the mass is equal to pressure times volume divided by the gas constant times temperature. Okay? Now I got the pressure, I got the volume, the pressure so let's evaluate this at state 1. Let's evaluate this at state 1. So that's equal to P1 V1 over RT1. I have the pressure, I have the volume, and I have the temperature at state 1. They are 0.25 megapascals, 3 cubic meters, and 500 degrees Kelvin. We're going to have to be careful of units here. Have to be a little careful with units. So let's see here. 0.25 megapascals. And the volume is 3 cubic meters. Oh, the gas constant for air. Well, the gas constant for air is going to be the universal gas constant. R universal divided by the molecular weight for the air. So let's look at that. The gas constant is 8.314 kilojoules per kilomole degree in Kelvin. And the molecular weight for air, let's look that up again. There we go. Air, 28.97 kilograms per kilomole. So this is going to be 8.3 kilojoule per kilomole degree in Kelvin divided by 28.97. 28.97. Make sure I have enough chalk here. Kilograms per kilomole. Okay, the kilomoles cancel out and I get kilojoule per kilogram degree in Kelvin, which is the unit for my gas constant. Temperature, T1 is 500 degrees Kelvin, okay? Notice the kelvins cancel out in the gas constant, okay? Now for the units to work out right here, this megapascal has to be expressed in terms of kilopascal, so it cancels out with the kilojoule in the gas constant. So let me convert out of the mega. So there's 1,000 kPa per 1 megapascal, and the megapascals will cancel out, okay? Let's see what the mass is. Let's put that all in the calculator and we'll see what we get. We'll see what the mass is. Let's see here. So 0.25 times 3 times 1,000 divided by 8.3 divided by 500. I'm going to multiply that by 28.97. And I get 5.23 kilograms. 5.23 kilograms. Okay? A Pascal is a joule per meter squared. No, joule per meter cubed, sorry about that. Or a Newton meter per meter cube or Newton per meter squared. So the pascals and the kilojoules and the cubic meters, these guys all cancel out, okay? So 5.23 kilograms. So now I got the mass. 5.23 kilograms, and U2 is equal to 214. 214.07 minus 359.49. And these both have units of kilojoules per kilogram. Notice the kilograms cancel out, and I get kilojoules here. So I'll get Q1 to 2 in terms of kilojoules. Let's see here. 214.07 minus 359.49, and that's going to be multiplied by 5.23, and so I get 760 kilojoules. Negative, sorry, there's a negative sign here because U2 is less than U1. Negative 760 kilojoules. Negative 760 kilojoules. Okay? So let me write that up here. Negative 760 kilojoules. Q1 to 2 equals negative 760 kilojoules. What does the negative sign mean? It means heat is being transferred out. Oh, sorry. There you go. Molecular weight, universal gas constant, did the unit cancellation, 5.23 kilograms. I got the mass now, 5.23 kilograms. I plugged in my internal energies that we just looked up, and I get negative 760 kilojoules. Why the negative sign? Heat transfer is out of air, or if you like, from / out of air. Heat is being extracted from the air, okay? We defined heat transfer as being in positive, so we got a negative sign, and what that means is heat is being transferred out of the system, okay? By the way, we can check this problem doing sort of a back of the envelope check to make sure our numbers are right. We can use specific heats. Why don't we do that? Why don't we do a little back of the envelope problem? Let me get rid of this. Let's do a little check. Let's do this problem in another way to get an approximate answer. Here's our mass. I'm going to leave that. So let's not apply the energy balance, but let's use specific heats. So recall, CV is equal to delta Q over M dt. So that's the definition of specific heat at constant volume. We have a constant volume process going on here. It's in a rigid container. So I can solve this for del Q. Del Q is equal to CV M dt. And I can integrate that. And I can integrate it. So Q1 to 2 is equal to the integral of del Q from state 1 to state 2, which is equal to the integral of specific volume at specific heat at constant volume times the mass of my system times dt. And that's from T1 to T2. Now I'm going to do a little hand waving here. And I'm going to assume constant specific heats. Let's see if we can assume constant specific heat over the process to at least get a ballpark answer. So let's go look at specific heats for air. Specific heats for air. Superheated vapor table, specific heat, air. So we go from 300 to 500 degrees Kelvin. If I evaluate CV at 400 degrees, which is the average temperature, notice it's not really changing a lot between 3 and 500. It looks like maybe about 5%. I'm going to assume CV evaluated at 400 degrees, and I'm going to use it to calculate my heat transfer, to estimate my heat transfer. 0.726 kilojoule per kilogram degree in Kelvin is my specific heat. So I'm going to evaluate this guy. I'm going to let this be the average specific heat, and then I can pull the mass and the specific heat out of the integral. Approximately equal to CV at T average, which is 400 degrees Kelvin, times the mass of my system times the integral of dt, which is delta T. Delta T 1 to 2. Okay? So I got Q 1 to 2 is approximately equal to the mass times CV evaluated at 400 degrees Kelvin, which is my average temperature. And then I have delta T, which is T2 minus T1. I have the mass, CV again. Let's see here, what was CV? 0.716 as I recall. CV at 400 degrees Kelvin, 0.716 kilojoule per kilogram degree in Kelvin, and that's from table. Make sure I got the right number here. Oh, I'm sorry. I'm sorry about that. Let's share it one more time. Got the wrong number here. So CV for air at 400 degrees is 0.726, and that's from table B10. 0.726, sorry about that. 0.726. And that is from B, oh, I'm losing it here, trying to finish up. And that is from B10, from B10. Okay, let's plug in. The mass was 5.23 kilograms. Specific heat evaluated at 400 degrees was 0.726 kilojoule per kilogram degree in Kelvin. Notice the kilograms cancel out. And then I've got delta T, which is 300 minus 500, and that has units of Kelvin. The kelvins cancel out in the specific heat, leaving kilojoules. Let's see here, what do we get? Hopefully we'll get something very close to the correct value, which is the value using the property tables. Let's see here, 5.23 times 0.726 times 200, and that'll be negative 759.4 kilojoules. So the true value using the exact properties out of the property tables is 760 kilojoules. I probably did a little rounding there. Assuming constant specific heat evaluated at the average temperature, I get 759 kilojoules. So Q1 to 2, negative 759 kilojoules, and this is from specific heat. Okay, assuming a constant specific heat. This is a back of the envelope check for our correct calculated value. Good idea when you do a calculation to be able to do it get it from different means, okay? So let's get this cleaned up. The actual heat transfer is 760 kilojoules out of the system. And from constant specific heats, we verified that using the definition of specific heat, constant volume, it's an isochoric process, and we get 759 kilojoules, very close to 760, okay? Good check, good check. So I'm going to put a check right here, check, that looks good. If you want to go through and check that IGB is valid, I think you'll find that it is. The reduced temperature, the minimum temperature in the system is 300 degrees Kelvin. The critical temperature of air is what, 133 degrees Kelvin. So you're going to get a reduced temperature min greater than 2. And I think you'll find the pressure is what? What's the critical pressure for air? Is it 33 or 37 bar or something like that? 37 bar. Air, 37 bar. Our pressures, our maximum pressure is going to be P1, the pressure falls, is 2.5 bar, so we're definitely below 0.2. So IGB, you can check it, it is valid. Take care, ladies and gentlemen. That is all. I think I've gone a little over time. So take care.